Hi everyone and welcome to Education with Eleanor. Today we're doing a video on electric field strength and also the force that is put on an electric charge or a charged particle when it's going through an electric field. So if you like this content, press the thumbs up button and press subscribe below and the notification bell to get notified of more physics, maths and science videos. Let's get into it. So we want to calculate the strength of an electric field between two plates that are 6 centimeters apart and connected by a 120 volt DC supply. So we have our electric field and it's got a distance of 6.0 centimeters apart. Let's change that to SI units, so that'll be 6.0 times 10 to the negative 2 meters. And the potential difference between the field is 120 volts. Okay, so we want to know, how do we get the electric field strength? Well, the electric field strength comes from our equation. Electric field strength is equal to the voltage or EMF divided by the distance between the plates. Now, this voltage here, also known as the EMF is the electromotive force. Now, let's get this calculation. So we have 120 volts divided by 6.0 times 10 to the negative 2 meters, and that's equal to 2000 volts per meter. Now, that's one significant figure by the rules of significant figures used usually internationally. For the Victorian Certificate of Education, though, this is actually 4 significant figures, because any trailing zero, regardless of if there's a decimal point or not, is considered significant. So you've got 1, 2, 3, 4 significant figures. Now, in terms of the debate about whether you agree with that rule or not, I'm not debating it. They're the rules that we go by in our study design. Now, if we look at our original data, our distance between the plates is 2 significant figures and the EMF is 1, 2, 3 significant figures. So our least amount of significant figures is 2 significant figures. How do we write this? Change this to scientific notation. So you have 2.0 times 10 to the positive 3 volts per meter, and the alternative units are newtons per coulomb for an electric field strength. Now you're probably wondering, where did we get this electric field strength equaling the voltage divided by the distance between the plates? Well, let me just quickly click onto my other screen so I can see it. Okay, so first of all, we have force on a charged particle is given by F equals the charge of the particle multiplied by the electric field strength. Now, if we look at net force, we know that net force is also given by MA, mass times acceleration. So we know that acceleration is also the net force divided by the mass. So the next thing we can do is, if we substitute equation 1 into equation 2 here, then we will get QE, which is the force divided by the mass. So let's do some highlighting here so we don't forget. So QE being that force is also known as the mass, QE there. Alright, let's keep going. So the next thing that we also know is that we have energy. So the change in kinetic energy for a particle going through a field is also known as the work. So that's to move the particle a certain distance, and that's given by the charge of the particle multiplied by the voltage or the potential difference or the EMF. Now let's keep going. So this will equal So something we have to remember is that work is also known as force multiplied by distance, and we will have the force here, which is QE, which has been given to us here earlier. So I'll highlight that again. And then we've got the distance between the plates, D. And then if we keep going, this is our equation for the change in kinetic energy. Let's continue. So we know that work is equal to force multiplied by the distance between the plates. This distance can also be known as displacement, but in this case we've got a uniform electric field, so it's the distance between the plates. So our work is given by QED, so the charge of the particle multiplied by the electric field strength multiplied by the distance between the plates. And we know that the work is QV as well, so we can substitute that in. So QV is equal to QED, and we can see that there is the charge of a particle on both sides of the equation. That will cancel out to 1, and so we've got the EMF or voltage is equal to the electric field strength divided by the distance between the plates. We rearrange to make the electric field strength the subject, so that will be voltage divided by distance. And that's how we get our derivation of formulas. All to do with electric fields. Let's continue. We now want to consider, if we have this same electric field, what is the force experienced by an electron that's going parallel to the direction of this electric field? So, first of all, we're being asked for the force, so that will be force on a particle is the charge of the particle multiplied by the electric field strength. And this is an electron, and it's going parallel to the magnetic field. Now, this electron will be going towards the positive terminal because that's where it's attracted to. So it's going in the opposite direction to the field line drawing that I have here, because the field lines will show the direction of a positive particle. So let's keep going. Now, the force on this particle will be the charge of an electron, which is 1.6 times 10 to the negative 19 coulombs, multiplied by the electric field strength, which we just calculated, which is 2.0 times 10 to the positive 3 volts per meter. So the answer is, the force is 3.2 times 10 to the negative 16 newtons, and it will be towards the positive terminal is the direction. Now, some other things that we need to know about. This electric field is constant and uniform between the plates. So you can see that the field lines are parallel to each other. So you have uniform acceleration along the field. And the next thing that you also need to know is that the force on the particle in a uniform electric field is constant throughout the field. And if you think about it, because we have force is equal to, oops, let's make that black, not red. So the force on the particle is the charge of the particle, and it's multiplied by the field strength. The charge of the particle stays constant. That's not going to change. An electron is electron, it always has 1.6 times 10 to the negative 19 coulombs of charge. And then if you think about the electric field is also constant because it's uniform. Look at the field lines, they're parallel to each other. So the strength of the electric field is constant and uniform throughout this kind of setup where you've got two plates parallel to each other. So if the charge doesn't change and the electric field strength doesn't change, then the force on the charged particle will always be constant. So that's something that you have to remember. Or that's the why behind it. Let's keep going. So what happens to an electron when it enters this same electric field, but it has a velocity perpendicular to the direction of the electric field? Well, it has trajectory motion. So if we look here, this trajectory motion looks almost like circular motion as well. It's got that similar idea, and it's because this electron will be perpendicular to the field, so it has a component of uniform velocity perpendicular to the field. It also has uniform acceleration, and I'm going to draw it the opposite way because it needs to be going towards the positive terminal. It'll have, and I'm going to fix this trajectory because I drew it the wrong way. Whoops. So this electron will be going towards the positive terminal and it has the uniform acceleration parallel to the field here, like I've written there. The trajectory in this case would look it would look the other way, because you do a vector addition and you'll get something that'll look like this. So that will be the trajectory motion. So that's why it's got trajectory motion, and it's because it has the uniform velocity perpendicular to the field, and it'll have a uniform acceleration parallel to the field. So this is an important consideration when you're looking at the movement or the direction of movement of a charged particle going through an electric field. So I hope you liked this video, and press subscribe and the notification bell to get more notifications on more physics, mathematics and science videos, and press the thumbs up button if you liked this video. This has been Education with Eleanor, and bye for now.